Yeah, we'll just pass them up and I'll grab them. We'll just make a stack. No need to put me into feedback. I don't think it matters. I did put a spot reason. I guess that's something I had in mind. And as always, if you do realize you had something else to say, I'm happy to hear it in terms of what you expect or don't expect or whatever from the class. So thank you for that, and we'll get right to it with some fundamental chemistry topics. So aquatic chemistry the theme is pretty obvious, chemistry of water, but we will touch on issues or topics that we might at first think have nothing to do with aquatic chemistry, like gas phase chemistry, for example. And in the corner here, we see a good illustration of when maybe the two might meet, right? So there's some special reaction that happens when you take a soda bottle, especially Diet Coke, and you add Mentos. It goes kaboom. And that has a lot to do with the dissolved gases there, right? So something about that Mentos candy is triggering a very rapid off-gassing of the CO2, converting it from some sort of dissolved CO2, carbonate form, and sending it out as gas, almost all at once. So you get that kind of explosion, geyser. Okay, so there are times that we're going to look at that, and I have to pick a little fun at the author here, and make a comment on his approach. So he brings up the carbonate system and the potential problem of ocean acidification as we dissolve CO2 in water. Essentially what happens is we have CO2 gas, we mix it with water, H2O, we end up with H2CO3. It's actually a reversible reaction. We're going to talk, I think the book is kind of either assuming that or going to just clearly talk about reversible reactions later. So I kind of inserted a few slides on that myself here. As we develop the fundamental principles, we'll get more to it. But from there, we also have a reversible or equilibrium reaction between that dissolved CO2, and you can kind of see it's just H2CO3. You literally just added those to each other. So it's almost like you have the CO2 connected to an H2O, and the formula is H2CO3, right? So when you have H2CO3 and you dissolve that, and that's in equilibrium with water, you end up getting acidity, okay? So this is why the pH of natural rainwater, it's exposed to CO2 in our atmosphere, gets some CO2 in it, and I say rainwater assuming there's really nothing else in it. So if we just take absolutely pure water and expose it to the atmosphere, it'll become slightly acidic, typically around pH 5.6 with our current amount of CO2 in the atmosphere. So it is a legitimate concern. How is this going to impact things if CO2 in our atmosphere increases? However, the author of this nice chemistry textbook is only looking at one side of the equilibrium reactions and gives an example a couple moments later that sort of counterbalances his concern that when we add acid to the ocean, different organisms that require a certain level of pH to keep their minerals intact, so there's a lot of diatoms and things like that, anything that makes a shell, we have some concern that if you lower the pH, it will start dissolving, right? So that legitimate concern, and that could make a very big impact on all sorts of ocean systems. Thankfully, however, but he kind of maybe got lost in his activism, there's another reaction that's very important to these carbonaceous calcium carbonate systems, which is the solid that those organisms are forming, calcium carbonate, relies on how much CO2 there is in the water. So if you add more CO2 to the water, it makes that precipitation reaction more favorable. So if you change the pH, but you're also making it more favorable, they sort of counterbalance a bit. So thankfully, that's probably not as much of a dire concern as he was making it out to be. However, he's using these different examples to say, oh, okay, when might it be relevant? And sure enough, these are both relevant, and we want to be able to have a handle on all parts of this system to really think critically about what might or might not happen as we engage with the environment. So the first was acid-base reactions that he was discussing. There's an acid-base reaction. It's also a gas phase reaction that is relevant there, but he was focusing on that deprotonation, and we get that acidity. So H plus being a proton, that's what we typically consider as acid, right? If we are adding H plus, then we are adding acid to the water. The next example he gave was, or next type of reaction, so he's summarizing several different environmental examples here. Complexation reactions. So if we have, if we form some complex to make a new molecule, in this case, ferric iron with water to form this FeOH2+, kicking off a proton there. And this is pretty common type of reaction. It's pretty relevant when we ask ourselves, okay, what can we precipitate? You know, what might this react with? And why is acid mine drainage acidic? Well, here's one example. As soon as we react this ferric Fe3+ iron with water, that tends to complex and kick off a proton. So as we deal with the environmental challenge of acid mine drainage, why is it acidic, right? We're just digging up dirt. Well, it turns out there's specific reactions that contribute to that and can make that type of wastewater quite acidic. Okay, already mentioned this, but part C here, dissolution and precipitation reactions are quite important. So this is just one of a whole bunch of examples, and we'll get more into this later in the semester. But we have reactions where you can dissolve or precipitate different solids based on the solution chemistry. And we'll use this in water treatment sometimes if we're trying to remove mineral content. We'd be like water softening. We might add calcium carbonate at some points to provide the carbonate to get rid of something else. There's a lot that goes on and a lot of different dissolution and precipitation reactions. This again is also what we would call an equilibrium reaction. We often draw that with an arrow going forward and an arrow going backwards because it can go either way. Okay, a few more redox reactions where we have some change in the amount of electrons of a particular species. We would call it oxidation if something is stealing the electrons away. That's an oxidation reaction, or a reduction reaction if you're sort of donating the electrons. It's a good way to think about it. So if we have oxygen and H plus with something donating extra electrons, we can make water, for example. And we often will write these with an explicit electron in solution. That's not always technically or physically what's happening, but it's a good way to understand the transfer of electrons. And so in this case, these H pluses, they all kind of would like to have an electron, but they're also happy just being an ionic species. But if you force them to have an electron, then they want to go share that with something like oxygen. So you can get, if you have O2, dissolved oxygen, and 4 protons hanging around, you could make 2 H2O so long as you get the electron balance correct. And so then you'd have to essentially add those electrons to it. Okay, another example would be oxidizing Fe2+ to Fe3+. So, and there's a note there that you can say the oxidation reaction is meaning we're in some sense taking an electron away from Fe2+, right? And if you're lacking the electrons, then that means you have a more positive charge. What you'll notice, we'll cover this more later, is the charge is balanced here. We have a net 2 plus here on the left, and a net 3 minus 1 on the right is 2 plus total. So whenever we're doing these redox reactions, you actually can notice the same thing above, we end up with some charge neutrality. That's kind of one of the governing principles. So we'll see this in many, many cases. This type of reaction may be important to say, oh, can we precipitate Fe2 plus better than 3 plus, or vice versa? What can we do to change this, to oxidize or to reduce? Very relevant in groundwater, as well as maybe when we're bringing groundwater to the surface for drinking, how do we treat it? Okay, I mentioned this already, but the gas-water partitioning reactions, so CO2 dissolving in water to form carbonic acid, H2CO3, or volatilization of hydrogen sulfide, H2S. That's the really stinky stuff. This is an interesting compound because it is so toxic that humans have evolved such a sensitive smell to it that we can actually sense it way before it's toxic. So hydrogen sulfide is extraordinarily toxic to humans, but we find it in our well water, and oftentimes it's fine. Because at that level it's not toxic. The trouble is when you end up having it at concentrations where you're going to get a lot of sulfuric acid, which is bad, with different reactions, and just the molecule itself, I think, is toxic. But it's also a nuisance before it gets to the toxic levels because we don't like the smell. So it kind of smells like rotten egg sort of odor. Okay, but that will also volatilize and off gas as a gas from water. Okay, a few more absorption reactions. This could be generally referred to as adsorption typically, is how we'll talk about it. We can think of lead adsorbing onto some silica substrate or surface where it's not a very strong chemical bond. A lot of times we'll see this written as some surface with some surface sites, and then adding, let's say, the lead there. So we'll see it written in a few different ways, but it's kind of like the Velcro type of reaction where it's going to stick there. You could pull it back off, but absorption reactions are just kind of that way. And so here they're drawing this line here to indicate that, yeah, it's a new complex or new species, sort of, but we're never expecting this to become really a new chemical where we would say maybe SiPbO2 plus, right? We would never think of it that way where we're merging them into something that's then saying that way. So this would be like not the way to do that. Okay, so that's kind of a example of adsorption. We can also introduce organic materials or organic matter. We often will describe natural organic matter or dissolved organic matter, NOM, DOM, in systems, whether it's wastewater, and then we don't really call it natural, we call it dissolved. It's whatever the bacteria are producing, whatever happened to be in there, just organic material there. Or in nature, as leaves dissolve, soil material runs off and things, we get a lot of humic acids and tannic acids, things like that. Large molecules, clusters, small particles, whatever they are, really fine sediment, we can have adsorption reactions there. And in fact, sometimes we use clays intentionally for particular adsorption reactions. Okay, a lot of times those are negatively charged, so they might have some affinity to positive charge, and we'd have the same type of adsorption reaction. In this case, they're showing cadmium there as an example. Okay, so there's a good number of types of reactions we can look at. We're not necessarily going to cover every single one of them in depth. For example, the absorption reactions, I go deeper on those in the class I'll teach next semester, and on the surface chemistry, but we'll talk a little bit about it with the colloidal section towards the end of this semester. Redox we will cover pretty heavily, and we'll have a couple lectures on that gas-water partitioning and really dive a bit into the CO2 system, especially as it relates to solubility and precipitation stuff that we might be interested in. So just kind of looking back through these steps, acid-base reactions we definitely need to get down. Dissolution precipitation reactions. We'll probably talk a bit about the complexation reactions, although I'm not sure if we'll spend a lot of time focusing on that. That'll be with the metals. Metals and ligands, I think, will be where we'll see that primarily. Yeah. Okay, so that's kind of a big picture of the types of reactions we've got going on. And now I want to come to, okay, the basics of expressing concentrations and really just talking about what's in a given solution, typically of water. Okay, so just a quick reminder. I hope this is just boringly obvious for each of you by now, but just in case. Avogadro's number, that's 6.02 times 10 to the 23rd. That's a mole of something, right? And what I like to say is 1 mole is very much like 1 dozen. You know, we go to the store, we buy a dozen eggs, right? Well, in chemistry, we might have a dozen molecules of something, or we might have a mole of molecules of something, right? It's just a number that's indicating we use it to describe it's many of this thing. Maybe in the case of dozen, it's 12, right? In the case of mole, it happens to be 6.02 with an exponent. If 1 dozen of X is 1.2 times 10 to the 1 power, aka 12, right? We don't ever think of it that way or write it that way, scientific notation, but truly that's what 1 dozen means, right? So in the same way, 1 mole is very much like that. 1 mole of X is 6.02 times 10 to the 23rd of X. Okay, so then when we express concentrations, typically when we use the brackets here, so brackets around X would mean that's moles of X per liter. Now, we're going to get to some caveats here in today's lecture that maybe we might also refer to molality instead of molarity, but in dilute aqueous systems, they're pretty much the same, and this is just going to mean moles per liter. And we often give that a unit of capital M italicized. Really, it's moles over liters. Okay, so that's kind of the basics there, and just in case I didn't put this in the notes or anything, but we remember that if we look at the periodic table and we see like hydrogen as 0.001 or something in the periodic table, what this is referring to, and there's going to be like a 1 up here too. This is just the element number, that's how many protons are in the element. The number down here, that's the atomic weight. And we define the atomic weight as essentially how many grams per mole, grams of the substance are required before you get 1 mole. So the atomic weight of hydrogen is something like 1.001. The decimal is actually, normally we'd have a nice even round number, but occasionally a hydrogen will have a neutron involved, and then we have heavy, like a heavier one, but it only happens every 1,000 or so. So on average, it's a very small portion of hydrogens will have that extra. So anyway, that's the convention. And if we wanted to describe 10 grams of hydrogen per liter, then we could use the atomic weight to figure out, okay, how do we change the grams to moles and get moles per liter, which is very often what we're interested in. And while I'm expounding on that, we have to note that whenever we have a chemical reaction, we want to describe the number of atoms or molecules interacting with a number of atoms or molecules instead of the mass, right? For the I'm about to give a very basic introduction to the other class, just students who haven't had chemistry in years, and the civil program. And I always tell them, if you wanted to egg a car, you might use a dozen eggs. You don't use a ton of eggs because you have a ton of car. 2,000 pounds of car does not mean you need 2,000 pounds of eggs, right? It's a silly, stupid example, but it kind of sticks in your head, I think, or I hope. The reaction of some chemical is while there might be some influence about how heavy the molecule is or whatever that could affect the reaction rate, the overall reaction is not determined by the weight of these things, right? So it's always the number that we're comparing. And so even if in regulatory scenarios or engineering scenarios, we like to use mass because it's easier to say, okay, I'm going to add this much into there, I'll weigh it, toss it in. That's convenient and all, but we also have to approach chemistry pretty scientific in terms of specifically how much are we doing here. Okay, so then we have an example from the book, and we have some acid, and this is they're describing an acid HA, really meaning that an H attached to an acid, so A being acid, and the H being the proton on that acid, right? So have some acid that's going to have a minus charge, and this could be something like as simple as HCl, ending up as H plus and Cl minus, or it could be acetic acid or something where the A part is a little more complicated, but regardless, it's a very simple notation here. So if we take that, we could use molarity to refer to a couple things about this. First of all, we could say if we have 1 mole per liter of HA, then we expect to have added 1 mole per liter of H plus. We also are adding 1 mole per liter of the A minus if it all dissociates. A lot of times these will be, sometimes they'll be equilibrium, but let's say HCl, for example, gives us the H plus and a Cl minus, and typically completely dissociates in water. So it won't really come back meaningfully to HCl. So in this case, we might say we added some concentration of HA, and the book will give us a little caveat to say, well, since it's not HA anymore, then we can call it something different. We could say that that's going to be equal to the H plus, which is also going to be equal to the A minus. Okay, so if we add 1 mole of this molecule that has both of them, it dissociates. We have 1 mole of each of those species that dissociated, right? That's hopefully obvious there, but sometimes that takes a moment to sink in. The other thing we could say is if we do have something remaining, so in the case of H2CO3, this is in equilibrium, and we will definitely have some H2CO3 left, even though we have split some of it to HCO3 minus. So in this case, we might be interested in saying, okay, well, the total carbonic acid species, including the HCO3 minus and the H2CO3, maybe we want the total for both. So we could describe as the total of that particular A. So AT, the total here, we could describe as the concentration of, I'll just use the example here, H2CO3, plus the HCO3 minus. Now, had we calculated the amount that we added in the first place, that would also equal the total. So that's just the total. Maybe we added it, maybe it just exists. I'm just going to write it as total added to kind of keep an example going. So that's kind of what it's talking about. Both of these can hold true because then in the case where we have complete dissociation, the HA, we have exactly that amount of H added, and so on. Okay, does that make sense? Hopefully I didn't confuse that. All right. Hopefully I'll pretty much review so far. Okay, so what about this molality thing? We don't talk about it very often. It's been a while since I actually looked at what exactly it means, even myself. It sounds a lot like molarity, but it has an L here, right? And that is on purpose, it's not a typo. So molality is essentially a concentration based on mass instead of based on volume. This is actually quite important when we really get to the technical details of how the solutes are interacting with other things in the water or in the solution. Definitely doesn't have to be water, and in this, the book's covering this, of course, this is aquatic chemistry, but we also want to know on a theoretical basis, how would this happen in a solid, like a solid metal with some species in there? How is that interacting? How would a chemical reaction proceed there? Okay, the definition is going to be when you have molality, when you have 1 kilogram of a solution that contains 1 mole of some species X, that's 1 molal of X. And we typically denote that with a lowercase m italicized. Okay, so instead of having a mole per liter for molarity, this was going to be a mole per kilogram. So if m is 1, let's say 1m is 1 mole per liter, then 1 lowercase m is 1 mole per kilogram. Okay? Now, the reason it is so close to the same thing in water is because if we have a liter of water, almost by definition, if we put that at 5 Celsius, that should be exactly 1 kilogram. Now, at standard room temperature, 25 Celsius, it's going to be slightly under that. So there's actually a slight difference there, but it's so close that most of science and engineering just calls it molarity if it's a dilute solution. And because we could consider if we had like highly salty water, it's more dense, right? We've learned that from probably science class a long time ago. You can make a salt wedge where it's more dense and the fresh water floats on top, and this happens in the Mississippi and other places, estuary systems. So we could change that, but in dilute solutions, it holds pretty much true, and we kind of just ignore it and pretend like there's no difference. So in most of the chemistry we've ever touched, and honestly, most of what we will do this semester, we can effectively ignore it, but we want to first talk about why this could be important and what's going on here. Okay. All right, so that's I basically just said all that with in aqueous systems. So a lot of times when we're dealing with a system like this, the weight or the mass can become important for really defining what kind of action is happening between the molecules. That's where it becomes more important to use molality, and that's why if we're carefully deriving some sort of equilibrium constant, we really should attend to that. So the book is going to attend to that because we're using these equilibrium constants kind of everywhere. So that's kind of why we are describing it. And they do add an example here. So on the molal scale, so the moles per mass scale, you do not have to worry about any changes to volume due to changes in temperature and pressure. Okay, so if we're considering doing this, doing some analysis at a higher elevation or at a colder or hotter system. Sometimes your solution can change based on what you dissolve in it, right? Obviously the saltwater example. And another example would be glucose in water. While the molarity of glucose will change if you change the temperature or pressure, the molality will not. Okay, so if we just take one solution that's pretty simple and make some change, molarity is going to treat it differently than molality. Okay, so it's kind of an issue for non-standard situations or dealing with stuff like that.
You say that for dilute solutions, we can assume molarity and molality equal?
Yes, dilute aqueous solutions. Yeah. However, so in general, we will probably do that, but before we start assuming that, we're going to piece together how do we define these equilibrium values based on thermodynamics, which the molality is important for. So we will get there and do that, but we're going to talk about it a little first, basically. And I think it also gives some examples of at what threshold is it not dilute enough, right? So brackish water that's maybe 5 grams per liter of salt is probably not dilute enough to treat as the same. Okay, so we have an example, and I'm going to make you do a little bit of writing and thinking here, and we'll look through it. The book is kind of already assuming you know something about these equilibrium reactions and the equilibrium constants, and I kind of assume you probably do, but I went ahead and added some slides to elaborate on this and explain this just in case. But for the moment, I think even without remembering much about this, the equilibrium reaction shown here between water and its the H plus and the OH minus, the conjugate acid and base. Water can dissociate like that to a small amount of these two. That's defined by this equilibrium constant, the dissociation constant for water, which would be equal to this value on the right. That should be enough to get you going on this, and then I'll take a step back and elaborate on that. So give this a minute and try to calculate this problem. It says consider pure water at 25 Celsius and 1 atm. That's pretty much room temperature here. The concentration of H plus as well as OH minus in such water is 1.005 m, so that's molality, times 10 to the minus 7. So that's moles per kilogram. The density of liquid water under these conditions is 0.997 kilograms per liter. Like I said, it's very close to 1 kilogram in every liter. So the question is, what are the molar concentrations of H plus and OH minus? And using the molality scale, what is the value of Kw? Oops, sorry. All right, so for the first part of this, we should be thinking something like this. The 1 molal solution is 1 mole per 1 kilogram. And so if we have 1.005 times 10 to the minus 7 moles per kilogram, we can multiply that by the density. Just look at the units, right? We've got kilograms and kilograms, those should cancel, because what we're aiming for is moles per liter to report in molarity, right? So we're aiming towards moles per liter. This is the way to get there, just that units analysis. So then whatever the answer to that is, which should be pretty close to 1.005, just slightly under, right? So 1.003 or something, times 10 to the minus 7, should be moles per liter, and that should be equal to the H plus and the OH minus. Of course, this would mean we're exactly neutral pH. Then when we go to use the molarity scale, we can calculate, the molality scale, we can calculate Kw if we find also the concentration for water. So there's another question there, which is kind of an interesting one. What is the concentration of liquid water in water at room temperature? Now, oftentimes we treat this as 1, right? And molality, that should be exactly right. In molarity, if we did the calculation, we'll find that it's about 55 moles per liter. So here's the question: is in the moles per kilogram here? Well, we know that we have, it's pure water essentially, well, minus a tiny bit, but ultimately it comes down to being approximately 1 when we put it to it. So we'll let the book give us the formal answer here and say, so the H plus is equal to the OH minus. That's 1.005 times 10 to the minus 7 moles per kilogram times that density. So 1.002 times 10 to the minus 7 moles per liter. They're very close. And then Kw we could find by multiplying those two in the numerator. And in this case, the book is, I guess, assuming we already know this should be just 1. And if we stop and think about water for a moment, this is the basis of our solution, right? So it's the number of, let's see, moles per kilogram. Well, that also should be about 55. So I think the reason it's dropping out of solution here, or dropping out of the equation, let's see. I thought it was giving a technical reason. But when we have liquids or solids, we generally refer to the concentration as just directly 1 in our equilibrium equations. I'll check to see if the book has an elaboration on that, but a lot of times you'll see it written as liquid, and we know that that should be 1 exactly. Do you happen to remember, was there a more specific? Now, one thing we could say is almost the entire solution is water. And the amount that's taken away by the H plus and the OH minus is so small comparatively that you just don't even notice it. That's one way to look at it. But I didn't notice them provide a nicer explanation than that. They just drop it off here. I think it does have to do with, hey, this is the whole 1 kilogram is just water here. So, okay, that would leave us, if we kind of assume that goes to unity there, that leaves us with m squared as the resulting units. And perhaps, let's see, it's moles per kilogram, yeah. So that unit is kind of a funny one. Technically that's true, but usually we will just treat it as moles per liter type units, just so that it's easier to handle. So the book goes on to describe that, and we'll come back to that in a couple minutes. Okay, so just in case we need this I wanted to take a bit of a step back and give a more basic overview of what are these equilibrium reactions and how do we handle them. I mean, we just did handle one a bit, and we will go much deeper on this. So this will just be a little more review to make sure we are comfortable heading in this direction. Okay, so we often think of two different types of reactions. One is irreversible, and the other would be reversible. So an irreversible reaction would be like combustion, where we have just one arrow going one way. And these equilibrium reactions or reversible reactions, maybe we'll do two ways. So far, the book is just labeling them as two bars, maybe equals kind of thing. I'm not sure if they're going to keep that up throughout the entire book. I haven't looked forward yet. But I would often see it as something like this to denote it's a forward and a backwards reaction. And essentially, these can be a partial, the equilibrium reactions are almost always some sort of partial ionization or partial dissolution, where you could come back to maybe a solid or come back to a non-charged species. So when we add HOCl, bleach essentially, hypochloric acid, maybe we would add it like NaOCl, and then it will, that OCl minus that comes off will be then in equilibrium with HOCl. So when we have a system like that, we'll draw this, this double arrow. We have one reaction going forwards, HOCl proceeding to dissociate into H plus and OCl minus, and a backwards reaction where they come and recombine. Now, once we reach an equivalent rate of change, forward and backward, we reach equilibrium. Sometimes that takes a little while. Sometimes it's pretty close to instant. Okay, so if we add in something like HOCl or HCl, it probably doesn't take very long. Well, HCl probably fully dissociates, so bad example. Probably doesn't take too long, but certain ones, it takes a little while. The rates may just be a little slow. Some of these are pH dependent, as this one is the case, and some of them are not. We were looking at the precipitation of calcium carbonate, for example. There are pH dependent reactions involved here, but this one is not necessarily, aside from the fact that you need the CO3 2 minus, right? That part is because the carbonate there, you know, that part is pH dependent. Okay, so anyway, that's kind of the gist of a reversible reaction. We can express them in a few ways. If you want a little example video here, you can see a guy scooping water with different size scoops into different buckets, and you'll see eventually he reaches an equilibrium even if there's a different amount of water in each bucket, because the rate or the size of the cup is different, but eventually he's taking the same amount of water because a small cup is getting full every time and the big cup is only getting half full because he's hitting the bottom. Right, so just a little analogy to say, yeah, here we go. It's this much water going across. The rate has stabilized and equalized. Okay, so typically we describe it as on the left reactants, on the right as products. That's typical for all chemical reactions. And if we write some reactants and products as A, B, and C, and D, a lowercase a here in front would be the number of moles or number of molecules in that particular reaction. Then we can write the equilibrium constant as this guy. Noting that, like we showed with water, we tend to assume that a liquid or a solid, typically in the denominator there, would be just equal to 1, just unity. So the real action then is happening for anything that is a solute in that solution. And if we had 2 of A, that would arrive here as an exponent. Okay, so that's generally how we come about our equilibrium constants and how we approach them. So for the case of H2O liquid in equilibrium with H plus and OH minus, that's where we came up with some equilibrium constant. I'm going to call it Kw, is going to define that and say that's equal to H plus times OH minus divided by essentially 1. It's the liquid water. Okay. Make sense? It's kind of the convention there. Okay, when we look at how we reach equilibrium, like I said, this usually happens pretty quick, but it's about the rates arriving at the same production and destruction, the rate at which that happens. That might mean you have a whole lot of one and a very small amount of the other. So they might be imbalanced in terms of the total amount there, but at some point you just had a little bit coming across, maybe for the faster reaction because there's just so little of that part remaining. So the balance, this equilibrium constant can shift the amount in one category or the other, and maybe that's shifted based on pH, maybe temperature will shift that. Something in the system could alter that. In the case of pH, maybe that's shifting one of the components of the reaction itself in here, and maybe if it's like temperature, it's shifting the K itself. Okay, so both of those could be a part of what happens. The carbonate system is a pretty good example of equilibrium reactions in practice, where we have the carbonic acid CO2 dissolves in this form, and then at neutral pHs quickly equilibrates with bicarbonate, HCO3 minus, which is typically the dominant species at neutral or near neutral pHs. So then the carbonate up at the higher pHs is over here. And so you'll notice, as I was talking earlier about, okay, well, how much carbonate is in the system? The concern for ocean acidification is, well, if we need CO3 2 minus and we lower the pH, we're dropping that off quite a bit, so we don't have as much. So it is true, if we dropped the ocean pH to 6, there would be massive, massive problems and diatoms could not exist, right? But if we're talking about shifting it just a tiny bit from here to here, well, we also ought to consider how much more CO2 do we have because we added CO2. You know, that was missing in that discussion, and it's not clear to me which one would counterbalance the other. And in the ocean system, there's a good chance we have enough buffering capacity that adjusting CO2 from, for example, 400 ppm, and maybe this will be a good problem for us to solve, even to, let's say, 500, I don't know how much pH change that would be with the amount of buffers and other contributors to the acidity in the ocean, but I'm a little doubtful that that's going to make a huge impact on the pH directly, since there are so many other things happening. But that's something maybe we can calculate. And on the flip side, it's also possible that then we might have easier precipitation of calcium carbonate that way, which would then remove CO2 from the system. So there's a lot more that goes on there. It is a legitimate concern, but it's just a complicated system, right? That's kind of my point. Okay, so what about pH? Just another kind of reminder here. Well, the P in pH we can use in a variety of different spots, and we'll see it also in equilibrium constants. We'll often see pKa instead of just a Ka, or I guess for water we could say pKw. Really, the P is a function. It's a mass function that just means we're going to take the H, or we'll say x, P of x is negative log of that x. Okay, so when we take P of H, really what we're saying is P of bracket H, the molar concentration of H. And so if we say that is 7, then that means we've taken H plus. H plus will equal 10 to the minus 7. Right? It's just that mathematical term. And if we reverse, so if the P is a negative log, so 7 would be equal to negative log of H plus. That means H plus is equal to 10 to the minus 7. So it's just this mathematical framework, but it's good to know and be familiar with so that we can say, oh, the pKa is 5, right? We could say that and then recognize, okay, here's how I need to treat this system. Okay, so in the case of water, the partitioning coefficient or the equilibrium constant, whatever we want to say, is about 10 to the minus 14. In fact, in the slides a few minutes ago, we calculated it to be, or the book calculated it to be 1.01 times 10 to the minus 14, right? So it's very close to that, and in the pure ideal case where we have maybe 5 Celsius, so exactly 1 kilogram per liter, we can say it's 10 to the minus 14. Okay, so then at pH, we know that we have a neutral condition, and that means H plus is going to be equal to OH minus. That is what we mean when we say that. And we also notice that 10 to the minus 7 is a special number because if we have 10 to the minus 7 times 10 to the minus 7, that gets us to 10 to the minus 14, right? So that's our square, essentially, that, you know, when these two are equal, we are neutral in terms of pH. Okay. Any other questions, issues there? Does that make sense? Okay. All right, so a few other, kind of back to the book now, a little overview, make sure we're all on the same page there. Another thing we could look at in terms of expressing a concentration would be formality. And at the risk of making a pun, this is sort of just a formality in my mind. So the formula weight, we already actually covered this in a sense. We used the example of some acid, and I think they use glucose versus sodium chloride here, or maybe acetic acid somewhere. But let's talk about the bleach example. So we have HOCl dissociating into H plus and OCl minus. Okay, so when we have this scenario, well, I'm going to write it this way. We might look at that total amount of molecules containing OCl, right? And in fact, maybe we added it as NaOCl. And then it dissolved from there. So if we go from NaOCl to Na plus and OCl minus, we might be wanting to describe the amount of moles per liter. And we could say, oh, we added 1 mole per liter of NaOCl. But we don't have NaOCl in solution. As soon as it's in there, it dissociates. And then it goes through this other reaction. So instead of saying, oh, we have 1 mole per liter of, let's say 1 mole of NaOCl per liter, is just technically not correct because that doesn't exist in solution. So the whole point of this is just that this is one formula weight of NaOCl. Okay, that's kind of all it's saying. We're just being a little extra formal about it, and that's all that we're doing. Okay, so the examples here, we have some given material, weight of the formula unit of that material, whether or not it actually exists as a molecule. So oftentimes we just don't even bother with describing this as formula weight, but we'll see it sometimes here like that. Okay. All right, a couple other things. We have mole fractions, whereas if we have a pure solution, let's say pure water, the mole fraction is 1. Pure gold as solid, the mole fraction of that solid would be 1, right? So this is a little more often used with gas phase stuff. So we might say the fraction of the atmosphere, we have what, 78% nitrogen, or was it 72 something? And we might say, okay, the fraction then, mole fraction is 0.78. There we go. But we can technically use that in here as well. Okay, let's see. So gave a couple examples. Occasionally we'll use it. It's really the number of moles for a given species divided by the total number of moles that are there. So it's a little bit like the molality in that it's like, okay, the moles per this mass, but now we're doing moles per moles. Okay, and this gives us a fractional unit, even if we don't know exactly the specific units of the total. It's just moles, right? So it's a number. Okay, so let's do another example. We can convert from ppm to molarity. And before we really dive into it, let me just explain ppm, ppb, ppt. These are common acronyms meaning parts, and this can be by volume or by mass, typically by mass. Per, that's the pp, and then it might be million, billion, trillion, sometimes thousand if we do that way. And what you have heard of probably the most, but also the least at the same time, is parts per hundred. So if we were to do parts per hundred, there's actually something you've seen for a very long time. That's a percentage, right? So then you can actually talk about parts per thousand, and the common way to do that, to express that, is actually the percentage sign with two little guys down at the bottom. So you've seen this concept a lot and just never knew it that way. So when you start thinking about it, yeah, what do I do with parts per million? Just remind yourself it's parts per, it's percentage, but instead of cent, meaning 100, like cent literally is the Latin root for 100, you are doing parts per something else. Okay. All right. So then example 1.8 says converting ppm to molarity. Consider a sample of fresh water at 25 Celsius and 1 atm, for which the total dissolved concentration of inorganic mercury, Hg, is measured to be 0.004 milligrams per liter. In this case, they're doing parts per million as mass, because now we see that's 0.004 ppm. Milligram is 1,000th of a gram, so parts per million is we're talking about 1 millionth instead of 1,000th. Or excuse me, I completely said that. Pardon me on what I just said. The thing is, when we take a look at a liter, that's a kilogram. So just ignore what I said. We'll just have to work this out. It'll make sense. So measured to be 0.004 milligrams per liter, which corresponds to 0.004 parts per million. This is double the current US EPA maximum concentration limit. The atomic weight of mercury is 200.59 grams per mole. Question is, what is the concentration of mercury in the water in units of moles per liter? Okay. So give that a couple minutes, and then we'll wrap up with this example. All right, good on that. So just to clarify what I stumbled over a minute ago. If we take a look at ppm as mass, sometimes we would take it as volume. That's usually more so for gas phase. But as a mass fraction, a weight fraction, what we're talking about is 1 ppm is 1 gram per 1 million grams of something, right, or of total. So if we had 1 gram in 10 to the 6 grams, that's the same thing as, if we're saying that's the same thing as 1 milligram per liter, that makes sense because 1 liter is 1 kilogram, 1 milligram is 1,000th of a gram, and 1 kilogram is 1,000 grams. So that ultimately leaves you with 1,000th of 1,000, which is 1 over a million. Okay, so all that to say, that's probably a confusing way to say all that. So let's just take a quick look at the solution here. That wasn't even the point of the problem, really. So this is just kind of make sure we're up to speed on the basics here, the practicing. So 200 grams per mole corresponds to that times 1,000 milligrams per mole, corresponding to 1 mole per blah, blah, blah. And so when we do that calculation, we can end up with 1.99 times 10 to the minus 8 moles per liter. So really just converting the mass concentration given the atomic weight and coming up with a moles per liter. Yeah.
So the conversion down here doesn't work for just water or
Down here? This is specifically water because 1 liter of water is 1 kilogram. So I'll make a note, 1 liter of H2O, that's what we were saying earlier, that it's approximately 1 kilogram per liter at standard conditions. really we did that problem, it was 0.997, right? And so even the book here, after describing how we can be technical about it, just kind of makes this assumption. So you'll see we kind of let go of those assumptions pretty quickly as soon as we're solving some practical problems. So technically this would be correct. So this is at 25 Celsius. This is true at 5 Celsius. So we often go ahead and use it. And we can do a lookup table for that and things. So yeah, that will be different if we were doing a question about how, let's say 5 ppm in ethanol or something. That we'd have to account for that for sure. And sometimes you will have problems that are like, what do we do in a batch of gin or something that's 40% alcohol? Oh, the density just changed, right? So that could become relevant. Okay, so that's all I'm going to do for today, and we'll see you guys next Tuesday. And have a good Labor Day and all.